In this video, we talk about Cauchy problem. In Cauchy problem, the domain X is from minus infinity to infinity. Previously, we saw that we can convert this problem into a parallel problem containing W. So we saw that A was equal to R omega or lambda, some people call it lambda, R inverse, and W is equal to R inverse Q. One should remember that here Q is a vector. It is a column vector. Column vector. For example, we have Q that is Q1, Q2 up to Qm. Similarly, this A is M cross M matrix. R is the matrix containing right eigenvectors, so on. We already saw this in our previous video. I'm not going to repeat it. If you just follow my lectures, you can understand that what's going on. So first thing is we need to convert this problem, which is a Cauchy problem, into the omega. So we saw that it was equal to partial W by partial T plus lambda partial W by partial X, that is equal to 0. Since we know that R is RW is, from here we can write RW is equal to Q. So what we get from here, if we multiply this with RQ, RQ X0, to convert our Q problem, that problem which contains Q into W, we should have W0 that will be equal to R inverse Q0. So we just replace this Q naught into W naught, and we know that we have this connection. Okay. So this is also a vector form. This W is written as a vector. It is a vector. It is basically a column vector. Let me just show you the components of this W. These will be equal to W1, W2, Wm. Since we are talking about the end element as mth element, this lambda is the matrix with eigenvalues lambda 1, lambda 2 up to lambda m, so on. So we converted our problem, this problem, into the relevant or corresponding problem in W. In scalar, in component form, it can be written as partial Wp by partial t plus, since this lambda contains eigenvalues, when we multiply this matrix with W, we get lambda p partial W p by partial x is equal to 0. So it means that we have lambda p partial W p by partial x is equal to 0. This is the scalar form. For example, if I have p is equal to 1, then we have partial W1 by partial t, first eigenvalue partial W1 by partial x is equal to 0. We want to convert our original problem into W since we want to compare this with the advection equation. You remember that in advection equation we had partial q by partial x is equal to 0. We have equation like this. These are m equations and this one is only one equation. So it means that when I put p is equal to 1, you get first advection equation. When we have p is equal to 2, p is equal to 2, then we have second advection, so on. We have m advection equation. That is the reason that we want to convert this system of equation into the decoupled advection equations. We know that if we have a solution of advection equation like this is our advection equation and the solution contains, for example, q x minus u bar t. So similarly, this solution, the solution of this system of advection equation must have initial condition move towards right or left depending on the eigenvalues. So the solution will be Wp x t is equal to Wp x minus, since we have this as u bar, that will be equal to lambda p t initially, and this means that w0p x minus lambda p t. So we put this will be equal to x minus lambda pt initially. It just means that your initial condition moves towards right or left depending on eigenvalue. Or we can write w0p x minus lambda p t. It means that your initial condition has just moved towards right or left. So this is the solution of this convert problem. For example, if we have partial w1 by partial t, lambda 1 partial w1 by partial x is equal to 0, then our first solution will be w1 xt is equal to w01 x minus lambda 1 t. Similarly, when we have p is equal to 2, partial w2 by partial t plus lambda 2 partial w2 by partial x is equal to 0. For this advection equation, we have second solution w02 x minus lambda 2t, so on. I hope you understand this point. Remember that our original problem is this one. This has unknown q and we need to find this q. Mathematically, we wrote this problem into w. So when we solve this w, we need to convert it back to q by using this transformation, by using this equation. For example, if we know what is w, then we can find q from here. By multiplying both sides with r, you get q. So r is known. Why r is known? Since it contains right eigenvector. And w is the function, characteristic function. So it means that the solution of this problem is this one. When we put for every eigenvalue or every wave, we put this value over here, then we get the solution q, which is required from this equation. Okay, we got the point. But let me just talk about how we write the solution. This is a Cauchy problem, but we can have reduction equation as well. Remember that q will be equal to r w. Where did we get this equation? Simply multiply both sides with r, we get rw is equal to q. Now we know that what is r? R is the column vector of all the right eigenvectors. For example, the first eigenvector is r1, 1, first eigenvector, second component, first eigenvector, mth component. Similarly, second eigenvector, first component, second eigenvector, second component, second eigenvector, mth component. And if we continue like this, we have mth eigenvector and its first component, mth eigenvector, second component, mth eigenvector, mth component, so on. This is very important step. You need to understand that. Otherwise, you will never understand this whole concept in future. And on the right hand side, W, remember that there are MW. For example, here we have W1, W2, so on. So the right hand side, on the right hand side, this one is W1, W2 up to Wm. Okay. What we do, we multiply these together. When we multiply, you know that this row vector will be multiplied with this column vector. We get R11 W1, R21 W2, RM1 Wm. Similarly, from second equation, second row, we have R12 W1 plus R22 W2 RM2 Wm. And the last one is R1M W1 R2M W2 RMM Wm. Okay, you got this point. Now what I can do, I can write this as R11 R12 R1M, and this one is W1 plus the second component, the not the second component but the second this term, this whole I want to combine it together. We get R21 R22 up to R2M, and we have W2, and the last one is RM1 RM2 RMM Wm. This is just a scalar function. It can move on the left hand side. Okay, so I write W1. This becomes W1, and remember that this was a eigenvector, and the eigenvector looked like this R1. 1 means the first eigenvector. So that is R1. Similarly, you can move W2 on the left hand side, and that is R2. Remember that R is a vector, column vector, plus this is Wm, and that is Rm. So we write this as I, not I, maybe P, since we will call this as a wave P1 to M, WP, RP, and on the left hand side we have QXT. That's how you write the scalar function, and which is a solution. You have uh, you actually got this W1, W2, WP, Wm from here, and R is already known. These are the eigenvectors. We multiply these together and we get Q, and the Q is the solution of this Cauchy problem. Thank you for watching.